Hello, in this session let us go through the module number 3 introduction part of Hydrodynamic Journal Bearings. So first of all, let us see what is hydrodynamic lubrication. So hydrodynamic lubrication is one of the type of lubrication which works under hydrodynamic principle. So here it is defined as a system of lubrication in which the load supporting fluid film is created by the shape and relative motion of the sliding surfaces. So here in this type of lubrication, the fluid film is actually created by virtue of the shape and due to the relative motion between the sliding surfaces. So the load carrying surfaces of the bearing are separated by a relatively thick film of lubricant in this case, so that there is no any metal to metal contact between the surfaces. So in this case, the film pressure, which is actually responsible to carry the load, is actually created by the moving surfaces, which pulls the oil or lubricant into a narrow zone called wedge shaped zone at a velocity which is sufficiently high enough to create that pressure, and ultimately the pressure that is generated will support the load acting on the bearing. Let us see the principle of hydrodynamic lubrication. As we can see from the figure, a hydrodynamic journal bearing or a full journal bearing which works on hydrodynamic principle. Now we can see from the figure number A, we have a journal or shaft at on the inside, and the outer one is the bearing, which is shown by the hatched portion, that is the bearing. Now there is this lubricant or oil which is filled. The clearance space between this journal and bearing is completely filled with the oil at all the times. Now initially, when the shaft is at rest, as shown in figure number A, so it sinks to the bottom of this clearance space under the action of this radial load W, and the surfaces of this journal and the bearing touch during this position, as seen from figure number A. Suppose if now the journal starts to rotate, okay, in the clockwise direction. So as this journal starts to rotate, it starts to climb the surface of the bearing as shown in figure number B, and there will be slightly a movement of this oil, okay, or lubricant in that direction. So as the speed is further increased, it forces the oil, more and more quantity of the oil will start flowing, and it will force that oil into this wedge shaped region as shown in the figure number C. So this is what the narrow zone, which actually is responsible for creating this pressure in this type of system. So since more and more amount of lubricant or oil is forced into this wedge shaped clearance space, pressure is generated within the system. So since the pressure is generated within the system due to the rotation of the shaft or journal, this type of bearing is also called as self-acting bearing. And whatever the pressure generated in the clearance space due to the motion of this journal with respect to the bearing, and that actually supports the external radial load W. So in this case it is not necessary to supply the oil under pressure. Only requirement is the sufficient quantity of the oil or supply of the oil. So the journal bearings which work based on hydrodynamic principle are called as hydrodynamic journal bearings. So as we have seen from the previous slides, in hydrodynamic journal bearing we have a journal, and the space between the journal and this bearing is completely filled with the oil or lubricant, and the film pressure is actually generated because of the motion of this journal with respect to the bearing. So the lubricant, when it moves into this narrow zone or wedge shaped zone, it starts to lift this shaft or the journal when the speed of the shaft or journal increases, and when the speed reaches the maximum, the shaft or journal will be completely lifted up, and there is no any metal to metal contact. The lubricant will be formed thick enough to separate the journal from the bearing. So this is actually done because of the rotation of the journal. So this hydrodynamic lubrication principle can be seen in many applications, like automobile engines, locomotives, aircraft engines, domestic appliances, underwater vessels, machine tools, pumps, gearboxes. So these are all the examples which consist of many machine components which depend upon the hydrodynamic films for their operation. So there are basically two conditions for the formation of this hydrodynamic film. So one is that the two surfaces must move relative to each other with sufficient velocity in order to generate that pressure so as to carry that load. And second, they must be at some inclination to each other. There must be some inclination. Okay? They should not be parallel. If they are parallel, then the pressure cannot be built up. So this is what the conditions. From the figure we can see in a journal bearing, when the speed increases to its maximum and the lubricant or oil flows and lifts the journal completely, separates the two journal and the bearing, and we can see from the figure the center of the journal is displaced from the center of the bearing by a distance which is represented by small e. It's called as eccentricity. So here, if there is no force that is applied to the journal, then it will be concentric with respect to the bearing. However, due to this load, the journal is actually displaced from its concentric position, and that is actually responsible to form that convergent narrow shaped zone through which the oil enters. And here the pumping action of this journal, when it rotates, it forces the oil to squeeze through this wedge shaped zone, thus creating that pressure. And we can see from the figure, the pressure falls to the cavitation pressure in the diverging zone or diverging gap, which is opposite to this converging gap, as we can see from the figure, the dotted zone. So the oil pressure actually creates that supporting force which separates the journal from the bearing surface, and the force of this oil pressure or pressure force and hydrodynamic friction force actually counterbalance the external load. So the final position of this journal is actually determined by the equilibrium between these forces. So in this part we will see what is the terminology of the hydrodynamic journal bearings. So from the figure you can see that the journal has moved into an eccentric position with respect to this bearing, and here there is a lubricant or oil film. When the speed of this journal reaches its maximum, the journal is lifted completely away from this surface of the bearing. There is no physical contact, and as we can see, the center of the journal has shifted. It is eccentric with respect to the center of the bearing, and this distance is called as the eccentricity, as we will see later. So small r is the radius of this journal and capital R is the radius of the bearing, or in other words, small d is the diameter of the journal and capital D is the diameter of the bearing, and this line is called as the line of the centers, wherein the minimum oil film thickness occurs. So we will see one by one. So what is diametral clearance? So diametral clearance, as the name indicates, is the difference between the diameter of the bearing, that is capital D, and the diameter of the journal, that is small d. So this difference, capital D minus small d, gives the diametral clearance. Similarly, radial clearance, indicated by CR, can be given by half of this diametral clearance, or it can also be given by radial clearance CR is equal to capital R minus small r. Next, line of centers. So as I said earlier, this is the line joining the center of the bearing and the center of the journal, along which we measure this eccentricity. So this minimum thickness or minimum clearance, called minimum film thickness, which is indicated by H minimum or H naught, occurs along this line. Okay. Next is eccentricity, denoted by small e. It is the distance between the center of the journal and the center of the bearing whenever the journal is rotating. So when the journal has moved to an eccentric position because of the load acting on the journal, and when the speed of the journal also reaches maximum, you can see this eccentricity between the center of the bearing and the journal. So next is attitude or eccentricity ratio, denoted by epsilon. So this is nothing but the ratio of the eccentricity E to the radial clearance CR. So that is given by this expression. And now if epsilon is equal to 0, that means there is no eccentricity between the journal and the bearing, and the journal runs concentric with the bearing. And if epsilon is equal to 1, then we can say that the journal touches the bearing. Next is minimum oil film thickness, denoted by H naught. So it is nothing but the minimum thickness of the oil film when measured along the line of centers, or the line joining the centers of the bearing and the journal, as can be seen from the figure. It is also denoted by H suffix minimum, H minimum. And one more term which we frequently use is minimum oil film thickness ratio, which is indicated by H naught by CR. So this is nothing but the ratio of the minimum film thickness of the oil to the radial clearance of the bearing. So from the geometry of the figure, we can write capital R as the eccentricity plus the small r plus H naught or H minimum. Therefore, R minus R is equal to E plus H naught. But R minus R is nothing but the difference between the radius of the bearing and the radius of the journal. That is nothing but the radial clearance. So if we substitute that, then radial clearance CR is equal to eccentricity plus H naught, the minimum film thickness. So now if I divide by CR on both the sides, then we will get the expression 1 is equal to E by CR plus H naught by CR. So since CR is the radial clearance, which is nothing but the diametral clearance by 2, diametral clearance is indicated by C, so therefore this can be written as, CR can be written as C by 2. So 1 is equal to 2E by C plus, again here C by 2 means it will be 2H naught by C. So this is the expression that we get. But 2E by C, that is this ratio is given by the term called eccentricity ratio or attitude, denoted by epsilon. So therefore substituting in place of 2E by C epsilon, and plus again this term 2h0 by c or 2h minimum by c is nothing but the minimum oil film thickness variable, that is delta. So we can write it this way: 1 is equal to epsilon plus delta, or delta is equal to 1 minus epsilon. This is the expression that we get from the geometry of this bearing. Next is the average bearing pressure in a journal bearing. So the average pressure in a bearing can be calculated by dividing the bearing load W by the projected area of the bearing. So projected area of the bearing can be given by the product of the length of the bearing or the journal and the diameter of the journal. So this product L into D will give us the projected area, and the load acting, if it is divided by this area, this will give us the pressure, average pressure.